So we talked about this when we were talking about word equations, and these steps apply to all types of reactions, in that we need to do this. You already have this part, or you should. Whoops, it's frozen. You already have this part in your notes. But we're going to write all substances correctly first. We're going to think about charge balancing. We're going to think about diatomic elements. And then we're going to add coefficients second. So that applies to everything that we're going to do. Now, this is the new part here. And it relies on, like I said, pattern recognition with the card sort. For synthesis reactions, for the most part, the ones that we're going to write, two elements are going to combine into a single compound. And as far as notes go, I would just continue with the notes that we've taken in these reactions. I would just have it be one thing, okay? We're going to have two elements that are going to combine into a single compound. And we're going to follow the steps in the proper order, meaning really what we're going to think about is we're going to look at these elements and we're going to ask ourselves, in what way would these combine? What would be the formula when these things combine into a chemical compound? So I'm going to show you some examples here. Na plus Cl. All right, so again, based on pattern recognition in the card that we just did, these are synthesis reactions. We're going to have one product. So what I think about is the charges that these things are going to form when they form compounds. So how about Na? What does it form? What charge? +1, thanks. Yeah, that's +1. And chlorine is over there in the -1 side. So when they form ionic compounds, they get those charges, okay? They're uncharged at first when they're elements, but they get those charges. So I need to write the formula with a balanced charge, which would just be NaCl. I'm not going to carry over the subscript 2 because this is the formula for NaCl, and you guys know that. So the first step is thinking carefully about what would this formula be, and then the second step is to go ahead and balance this with coefficients. So I put a 2 there to balance the Na, and then I put a 2 there. And so that's what that equation should look like. So it's all about that thoughtful step of how would these combine, and let's follow the rules that we know for writing equations that we learned last semester. So another example, this one's sodium. Sodium is +1, as we just saw. What charge does oxygen form? -2. So I would need 2 sodiums that are +1 apiece to match up with 1 oxygen. So again, all I'm thinking about when I write that compound is how would those things come together in terms of having a balanced charge, a charge that sums to 0, which would be Na2O. Once you do that, the second step is to balance with coefficients. So I got 2 oxygens here and 1 here. I'm going to put a 2 there. That makes 4 sodiums. So it should look like that. Questions about any of that so far? So what I would like you guys to do is just take a moment here and try these last two. If you're watching this as a video, just pause it for a second and see what you think. See if you can figure those last two out. Okay, so in looking at the third one, we are going to realize that magnesium is in the +2 column of the periodic table. Sulfur is in the -2 column, so they form +2 and -2. And so therefore they would come together just like that. That's already balanced, everything, that one's done. This one also, I just realized this is slightly different. Never mind. Zinc plus iodine. This one also, zinc is +2, iodine is -1. Now, I'm not writing that 2 because of this 2 right here. I'm writing it because iodine is -1. And so it's going to match it with 2 zinc. So hopefully you just didn't randomly write ZnI2 without thinking about it. If you did, you got lucky. But so that should be the correct equation there. Questions about that? So now let's go on to decomposition reactions. And these, I think, especially for the types that we're going to do this year, these should be the easiest to write. Really, the only way you could mess them up is to forget about the Bringelhoff elements. So really, with the exception of the one on this lab that we're going to do at the very end of class, the type of decomposition reactions that we're going to ask you to do are where a compound is breaking up into the elements that comprise it. There's definitely other decomposition reactions, but that's the ones that we are going to, that's the type that we're going to focus on tests and quizzes and things like that. So you're literally just looking at the thing, breaking it apart into its elements. If it's diatomic, put a subscript 2 on the thing. If it's not, don't. So again, same rules. We got to write every substance in the reaction correctly first. So calcium chloride is going to decompose into the elements calcium and chlorine. So my only job is to write those correctly. Calcium is not diatomic. So that would be a Ca, not a great A. How do I get? I don't know how to do my eraser. Ca. Chlorine being diatomic, I'm going to write a 2. I'm not writing a 2 because of this 2. I'm writing a 2 because of the fact that chlorine is diatomic. And then it's balanced and everything. The next one, that's strontium oxide. Strontium is going to break apart into strontium and oxygen. Is strontium diatomic? No. How about oxygen? Yes. So when it is decomposed, it's going to decompose as O2. And then from there, we would just put a 2 here to balance those oxygens. So that's our decomposition reaction. So the lab that we're going to do in the very last part of class today is going to be a decomposition reaction, and that's when you will see your example in person of that. Questions about that? So let's look at our last type that we're going to talk about today. Oh, whoops, let me skip this. We don't need this. Here we go. So combustion reactions. Combustion is a fancy word for burning. It's defined as an exothermic reaction with oxygen, meaning giving off heat energy. So that definition of combustion kind of can encompass a lot of different things. Like even for example, something like rusting could fit into that definition, that you're reacting iron with oxygen to make iron oxide. But that's not the definition that we're going to use. We're going to define it a little more narrowly as, and this is the way most people think about combustion. Again, combustion is burning stuff. And when we human beings, when we burn stuff, we usually burn either hydrocarbons or sometimes alcohols that have oxygen in them. But you react something with oxygen to produce CO2 and H2O. And of course, it is we burn gasoline and things like that, and we're doing too much combustion. We're getting too much carbon dioxide in the atmosphere. That's one of the things that's causing some problems right now. But so the pattern is this: you're going to have possibly what we call a hydrocarbon. Hydrocarbons are things that have only carbon and hydrogen in them, but it will always be plus oxygen to always produce CO2 and H2O. So combustion reactions actually should be the easiest ones to write, because the only thing that ever changes is the actual thing that you're burning, that you're combusting. Now, they can be challenging to balance. They can definitely be challenged to actually balance with coefficients. But as far as just to write them and get the reactants and products, that part shouldn't be, that part should be the easy part. Now, another one, and the reason I'm writing these patterns is because I want to really emphasize the fact that some people think that if the compound itself has oxygen atoms in it, that you don't need to react with oxygen, but that is not the case. And again, you guys know this. This is one of the first things, one of the early things you learn in science. You put a jar over the candle goes out. It doesn't have oxygen anymore. You have to have oxygen to burn things. Anything, it needs oxygen. Oxygen is equally as important. So let me present a scenario to you. I may have brought this up before, but just it's relevant now, so I'm bringing it up again. Let's say I did something crazy. Let's say I taped off this whole room. I turned on the gas. I opened up all of these spigots, and I let the gas just run for hours so that there was no more air in here at all. I pushed out all the air, replaced with natural gas. And then I take a lighter out of my pocket, and I light the lighter. What's going to happen? There you go. Yeah, actually nothing would happen, because if I really did push all the air out of this, there would be no oxygen, no burning will happen. I couldn't even light the lighter, and the room would not explode. Now, probably it would actually be very, very difficult to push all the oxygen out of this room, and so there would be some oxygen, and I would kill myself and other people nearby. But if you really could get all the oxygen out of here, no burning. So, looking at a couple examples here, and I'm going to show you some examples. I'm going to show you some demonstrations here in just a second. But this top reaction, the stuff that comes out of the gas jets mainly is natural gas, which is about 80% methane, this CH4. So, as I said, it's automatic and easy to write the reaction, the products of combustion. It's CO2 and H2O. As I said, they can at times be challenging to balance. We've looked at these already, whether you realize it or not. When we were practicing reaction balancing, we were balancing some combustion reactions. You definitely want to balance the oxygens last. I always go carbons first, then hydrogens, then oxygens. So like in this case, we got 4 oxygens on the left. I put a 2 there. The carbons were already balanced. So the total number of oxygens at this point is 2 plus 2 over here is 4. So if I just put a 2 there, that one is going to be balanced. C2H6O. So again, notice even though there's oxygen in this, I still need elemental oxygen to combust it. CO2 plus H2O are my products. Best way to balance these: carbons first, put a 2 there. Hydrogens next, put a 3 there. 2 times 2, 4 oxygens here, plus these 3, that's 7. Now, some people get a little confused when there's oxygen in this thing in terms of balancing it. So let me tell you the way that I would approach this. So I know I need a total of 7 oxygens on the left. Now I already have 1 because I have 1 right here. So in my mind, I'm thinking I need to get 6 additional oxygens. 7 minus 1 is 6. I need to get 6 additional oxygens on the left side. And the way I'm going to do that is by putting a 3 there. That's a 3. And so now that's balanced. That thing about, we ran into that before where you have an odd number of oxygens and you can't balance it. That doesn't apply in this case because of the fact that there's this oxygen here. So in this case, we actually can work with the odd number of oxygens. What I would like you to do is take a look at 148 for a second. So what 147 and 148 is practice with some of the different types of reactions that we've looked at, but there's something I want to call your attention to on the last part, the combustion reactions, the 21 through 25. So again, for like 21 and 22, for the products, we can write CO2 plus H2O, CO2 plus H2O. That part's easy. We do need to balance it. But if you're looking at one like 23 that says, for example, the combustion of C2H2, we can't forget, what else do I have to react this with to burn it? Oxygen. So you have to remember, even if it doesn't say or it doesn't put the oxygen there to start, you still need that in there. Now again, that's not balanced, and you got to balance it. Same thing with 24, C12H22O11. Even though there's oxygen in the sucrose, it still is not going to burn without additional elemental oxygens. So that's it for the new types of reactions you have to learn to write. So the rest of class is just we're going to do a bit of practicing, and we're going to do the lab in the very last part of class and some demos I'm going to show you in a second.